All right, welcome to the Explainer. Today we are going to tackle something that is quite literally shaping our future, semiconductor chips.
So how in the world do we take something as basic as sand and turn it into the powerhouse behind artificial intelligence? Let's get right into it. It's this incredible journey, really, from one of the most common things on the planet to maybe the most complex thing we've ever built.
You know, the heart of every single chip, whether it's in your phone, your laptop, or one of those giant AI data centers, it's all silicon. And where does silicon come from? Good old-fashioned sand. It's actually the second most abundant element here on Earth, right behind oxygen.
So this whole process is just meticulous. We take this raw, gritty sand and it gets purified to an insane degree. Then it's melted down and grown into this massive, perfect crystal cylinder called an ingot. And from there, that ingot gets sliced into these beautiful, paper-thin, mirror-smooth discs. We call them wafers. But they're not just shiny discs. Think of them as the perfect, pristine canvases where we're about to paint the modern world.
Okay, so we've got these perfect silicon canvases. Now what? Well, this is where the magic happens. We build billions, and I mean billions, of microscopic little switches on them. These are called transistors. And you have to understand, this is it. This is the fundamental building block, the single atom of everything digital.
Now, don't just think of a transistor as a boring on-off switch. No, a much better way to picture it is like a tiny, tiny faucet that you control with electricity. When you apply a little voltage to its gate, that's the handle, the faucet opens, and a current of electrons starts to flow. You take that voltage away, the handle turns, and the flow stops. That's it. Every single thing your computer does, from sending an email to training an AI, is just built on billions of these little faucets turning on and off.
But here's where it gets really clever. We don't just use one type of faucet. We pair two opposite types together. One turns on with a high voltage, and the other turns on with a low voltage. And when you put them together, you get this system called CMOS. And the seesaw analogy here is just perfect, because one is always on while the other is off. There's never a straight path for electricity to just wastefully flow through. One side of the seesaw is up, the other is down. This simple, elegant pairing is the secret sauce behind why our gadgets can run all day without melting or draining the battery in 5 minutes. You know, when you think about billions of transistors, you might picture them all laid out flat, like a huge city grid. But if we did that, a single chip would be the size of a dinner plate. So that's not what we do. Instead, we build up. Modern chips are these unbelievably complex, multi-story structures. They're basically microscopic skyscrapers.
Yeah, a top-of-the-line chip today can have as many as 20 different layers of metal wiring all stacked on top of each other. 20 floors in this tiny skyscraper. And to connect everything, to get the signals from one floor to another, they use these tiny electrical elevators called vias. It's this vertical building that lets us cram an insane amount of computing power into such a tiny footprint.
And actually building these skyscrapers, it's a marvel of precision. The whole process, from a blank wafer to a finished chip, takes about 3 months. And it happens inside these factories that are thousands of times cleaner than a hospital operating room. It's almost completely automated, all done by robots, because a single speck of human dust could completely wreck a chip with billions of transistors. They even use unbelievable amounts of ultra-purified water just to keep things clean between every single step. It's wild.
All right, so for decades, this whole industry ran on a pretty simple rule of thumb called Moore's Law. Basically, the idea that the number of transistors we could fit on a chip would double every 2 years or so. But here's the thing, we are now bumping right up against the fundamental physical limits. We're talking about structures so small we're counting the atoms, and that pressure is forcing some incredible next-level innovation.
And this slide just perfectly shows how we've had to completely reinvent the transistor to keep going. We started with these flat 2D transistors. Think of it like trying to stop water in a hose by just pressing down on it with your finger. Sure, it kind of works, but it's pretty leaky. So then came FinFET. This was a huge deal. It's a 3D design where the channel, the hose, is raised up into a fin, and the gate wraps around 3 sides of it. Now you're gripping the hose with 3 fingers, much better control. But today, we're moving to what's called gate-all-around, or GAA. And just like the name says, the gate completely surrounds the channel. This is like clenching your entire fist around the hose. You get absolute, maximum control, no leaks.
So why does all this matter? Why go to all this trouble? Well, here's the problem. As those little transistor faucets get smaller and smaller, they start to drip. They leak a little bit of current even when they're supposed to be off. Now, one leaky faucet in your kitchen? Not a big deal. But imagine you have 90 billion leaky faucets in your house. That's what we have on a single high-end chip. All those tiny drips add up to a huge amount of wasted power and, just as bad, a ton of heat.
Okay, so let's zoom out a bit.
Let's move from the microscopic to the global stage and see how this intense tech race is playing out. Because make no mistake, the ability to manufacture these leading-edge chips is one of the single most important geopolitical assets of the 21st century, period.
Right at the bleeding edge of this technology, it really comes down to three huge players. First, you've got TSMC in Taiwan. They are the world's biggest contract manufacturer. They make the chips that go into Apple's iPhones, NVIDIA's GPUs, you name it. Then there's Samsung in South Korea, a total powerhouse, and they were actually the first to get that new gate-all-around tech into commercial products. And finally, you have Intel in the US, the old giant, the company that basically started it all, and they are now pouring billions into a super aggressive plan to get back on top.
So how do we get here? How did Intel lose its crown? This timeline tells a really pivotal story. A decade ago, Intel was king, no question, but they got a little too comfortable with their old manufacturing tech, which is called DUV. Meanwhile, this Dutch company, ASML, was perfecting a revolutionary new machine called EUV. Think of it like going from drawing with a fat permanent marker to an ultra-fine point pen. It's just way more precise. TSMC saw the future and made a massive risky bet on EUV. Intel waited, they hesitated, and in that moment of hesitation, TSMC just blew past them. Intel's been playing catch-up ever since.
And then, of course, there's China. Their national champion is a company called SMIC. Now, because of some pretty heavy geopolitical restrictions, they can't buy those latest EUV machines from ASML, and that's put them about 5 years behind the curve. So what's China's response? They have poured unbelievable amounts of money and resources into building their own domestic chip industry. They see this as a matter of absolute national security. They've even dubbed the effort their own Manhattan Project.
Okay, so where does this all go from here? What's the next big move? The race isn't just about making transistors smaller anymore. The next decade of computing is going to be defined by these really bold new ideas in how we build the transistors and, just as importantly, how we power them. And what's so fascinating right now is that we see two totally different philosophies on how to win this next round. On one side, you have TSMC. They're taking the cautious, steady route. Step 1, perfect the new GAA transistors. Step 2, later on, integrate a new power system. It's a reliable step-by-step evolution. Then you have Intel. They're going for broke. They're making this super aggressive leap to do everything at once. They're introducing their version of GAA and a radical new idea called backside power delivery. Now this is a game changer. Right now, the wires for power and the wires for signals are all tangled up together on top of the transistors. Backside power moves all the power lines to the bottom of the chip. This creates a clean, efficient superhighway for electricity and frees up the top for much better communication. It's a huge risk for Intel, but if it pays off, it could catapult them right back into the lead.
Okay, so let's wrap this up. What are the big things to remember here? First, that going from simple sand to a working computer chip is, without a doubt, one of the most complex and expensive things humans know how to do. Second, it's not just about speed anymore. The whole game is about power efficiency. That's what makes AI data centers feasible and gives your phone all-day battery. Third, and this is absolutely critical to understand, the ability to make these chips is a massive geopolitical choke point. It defines who has economic and military power. And finally, the race to the future is on, and it's this epic showdown between Intel's high-risk, high-reward gamble and TSMC's proven, steady dominance.
So that leaves us with the big question. As we get down to the absolute physical limits, where we're literally counting individual atoms, who's going to invent the next big thing? The next breakthrough in this field isn't just going to give us a slightly better phone. No, it could literally redefine the global balance of power for the next century. Thanks for joining me for this explainer.